Welcome back everyone. Today I want to return to my beloved game Shellshock Live and the Aimbot project I started a couple of months ago. Basically, I'm trying to write some Python code that can make us hit every shot we take on the enemy tanks. Where we're at right now is being able to detect the tanks from a simple screenshot of the game, and then calculate valid trajectories to hit the enemy. Meaning we get the power and the angle, which are the relevant parameters of the shot. So in the last video we explored what it takes to write this aimbot and the physics behind it. It's my best performing video to date, so I really want to thank everyone for watching it, as well as leaving so many suggestions in the comments. And in this video I want to actually implement some of your ideas and improve the aimbot. As I mentioned in the previous video, our main goal today will be to add multiplayer. So make the code automatically detect the number of tanks and also actually find them. Luckily, we did some setup for that in part 1 with the k-means clustering algorithm. And then I turned towards the comments. Again, thank you all for the support and the many ideas you gave me. The two most common suggestions were to first account for terrain collisions, and to adjust our formula to also account for wind. Now, I feel like the ground detection is something we desperately need to fix, because right now our aimbot still doesn't care if we straight up just shoot into a wall. But what I'm really looking forward to is taking a look at the wind. It can have some really weird behavior, like turning around your shot, so the physics behind it should be interesting. Without any further ado, let's get right into it and start by looking at multiplayer. In the game, you can have up to 8 tanks, either divided into 2 teams or a free-for-all. So far, we've restricted ourselves to only a single enemy tank, but I want to generalize this to an arbitrary amount. Since the tanks are pretty distinct from the otherwise simple background, an obvious approach to detecting them would be to use image recognition or template matching. I even spent some time looking into a few Python libraries that could do that, but it all seemed a bit overkill for just finding a few tanks on an image. And then again, we've already laid out the groundwork for a color-based detection in the last video, so I'll just stick to that approach. The initial idea will be very similar to part 1, so I'm reusing the filter color function. If we take a screenshot from the game like this one, we can already eliminate most of the background if we only look for red and green pixels. These stray pixels from the color spilling into the names we can eliminate easily enough, as seen in part 1. So what we're left with are these bunches of tanks, health bars, and turn indicators. From those, we're obviously interested in the red enemy tanks and our green tank. For separating the bunches, we applied the algorithm from the last video. If you recall, it was called k-means clustering, and it worked something like this. Say we want to divide these scattered points into their corresponding clusters. Then, given some more or less random starting guesses, we'll color all the data points based on which one they're closest to. Then, for every color, we calculate a new mean and update the guess. It takes a few iterations, but then it should correctly find the clusters. If we go back to our screenshot from the game and apply the algorithm, this is what the computer sees. Here, the different colors show the individual clusters. And then we just go through them one by one and assign the tank type. A green cluster below a red one means a friendly tank, those we can ignore for the most part. And the green cluster above a red one means an enemy tank. Lastly, among the friendly tanks, we pick out our own tank through the largest green cluster. just for some housekeeping, I also had to make a few changes to the k-means algorithm since the last video. Because our tanks are so far apart on the image, it could sometimes happen that one of the clusters remained empty the whole time. Then we would effectively have one less cluster. So I implemented a failsafe. What it does is to take a point from the current largest cluster and reassign it to the empty one. Then we can run the algorithm again, and hopefully the cluster gets populated correctly this time. And because we can have multiple empty clusters, we repeat this failsafe until no cluster is empty. With this improved algorithm, we should now always find the tanks correctly. Furthermore, I am only considering distances in the x-coordinate, since the tanks are rarely above one another. So the y difference is more like a hindrance to the algorithm. But here's the thing. For this clustering to work effectively, the k value must match the number of tanks. So here it should be 4. Only then do the corresponding centroids, or means, make sense for targeting. But if we instead look at k equals 3 or 5, we can't use them anymore to accurately get the tank positions. Obviously, we could just pass in the number of tanks before every shot, but I would find it much cooler if the program could decide that for itself. To do that, we inevitably will have to compute the clustering for all candidate k values, and then find a way to put a number to how well they performed. So something like a score or a grade, where we can objectively choose the best one. And for that, I want to introduce you to the silhouette method to finding the best k value. Let's actually ignore all this maths here for a minute and try to come up with that algorithm ourselves. The idea is going to be to look at a bunch of clusterings for different k values and give them a score on how well they performed. Then we just pick the k value with the best score. For now, we can be a bit vague about it and say our score is how well a given point fits into its own cluster, minus how well it fits into the other clusters. If we compute the score for every point and sum them all up, we get a total score for this k value. Take this clustering as an example. Here we have a cluster consisting of 2 tanks. So while all the other clusters are relatively compressed, this one is more spread out. So the points fit less well into this cluster because the cluster as a whole is just very big. So it would score low on the first criteria. Similarly, for this image, one tank is sharing 2 clusters. And since they're very close together, for the points in those 2 clusters, it actually won't make much of a difference if they're in one cluster or the other. So here, the points fit well into another cluster, meaning we subtract a lot from our score, which again lowers it. I hope you see how this is an objective way to put a score to every clustering, because through the 2 parts, we punish both too small and too large clusters. It's actually a bit easier if we invert our grading system. So give a low score if the point fits well into its own cluster, and similarly give a high score if the point doesn't fit well into another cluster. Then, if the 2 functions swap places, we're still looking for the maximum score. Alright, great. So all we gotta do is define these functions that can evaluate these scores for a given point and clustering. So what does it mean for a point to fit well into a cluster? Or to formulate this a bit differently, how can we punish clusters that are abnormally large? Well, kinda per definition, a cluster should be a collection of points that are close together. So let's just use the distance from our point to every other point in the cluster as the score. Let's see it in action. For the blue cluster, the distances will all be pretty small, since it only spans one tank. And similarly for the green one. But for the yellow cluster, we will also compare points from two different tanks. This will cause the total distance to be much larger, thus punishing a low K value. But to be fair to larger clusters with more points, we'll also average it over the cluster size. Then for the other function, to grade how well our point would fit into another cluster. Here we basically do the same thing. Just pretend like the point belongs to another cluster, and again calculate the average distance. And to be rigorous, we pick the cluster that performs the best out of all. Alright, let's see what it does. So here we compare distances in between clusters. We take a point and measure the distance to points in another cluster. For well-behaved ones, like the blue one, these distances will be large. So even the minimum value is big. But while for the pink one, the distances to yellow, blue and green are large, the distance to orange will be very small. And since we only pick the minimum, this is what counts. Through this method, a larger K value will only return a low score. By punishing each extreme of the spectrum, we will find a maximum at an intermediate K value where the cluster sizes are just right. Now, to get to the form I showed earlier, we still need to divide our pointwise score by the greater of the two. That's to normalize the score to the interval -1 to 1. And if you go back, you will see that this is the exact same form of the silhouette method I've shown earlier. And here is how it looks in our code. If we run this function on the image with the 4 tanks, we indeed get the best score of around 0.9 for k equals 4. To save some precious computation time, instead of summing over the distances to every point of a given cluster and then averaging it, we just calculate the distance to the mean. I hope you see that if our data is well enough conditioned, this shouldn't make too much of a difference. So with the positions now determined, we can reuse the function from the last video to calculate the valid trajectories. Only now we do this for every enemy tank on the screen. The actual logic of this inner function is still the same as in the last video. We just compute a set of trajectories for every tank. I've quickly thrown together a visualization for everything, and I'll feed the program this image from a match. As you can see, it correctly identifies our tanks as well as the enemies. Then it suggests a shot to hit all 3 enemies. Alright, with a working multiplayer, I now want to fix probably the biggest flaw in my aimbot: detecting the ground. Most projectiles in the game explode on ground collision, causing the nearby terrain to change a bit. There are also a few weapons that ignore the ground completely, or where their whole gimmick is that they only go through the ground. But right now, I want to focus on the more conventional ones. Take a situation like this one. Here, the mountain blocks a fair bit of the valid trajectories. So ideally, we want a way to detect this ground layer before we take our shot. Meaning we have a function that at every x coordinate returns the height of the ground. Then, since we can represent the path our shot takes as a function as well, we can just see if the functions intersect at any point. A situation like this one would be bad, because we clearly hit the mountain, whereas no intersections means the path is clear. So how do we get that ground function? Well, to stick with the theme of this aimbot, I'm gonna resort to colors again. Up until now, we've ignored blue pixels, but we should be able to reuse the same function from before to detect them as well. We just have to adjust the hue, saturation and value ranges to get the best selection. And yes, I know there is also other color schemes for the ground, like this yellow one here, but I'm just gonna stick to the blue one, since all you would need to do is change the hue values for the color you want to detect. Except for if the ground is red or green, then I guess all hope is lost anyways. Okay, so we've detected all blue pixels. What now? Basically, we've got 3 steps to do. First, you can see that we caught a lot of stray pixels. We pick up the shield bar from our tank or parts of the UI. It's maybe a bit difficult to see, but basically we want to get rid of these red pixels here. We can do this by just selecting the largest contiguous batch of pixels. Thankfully, SciPy has an inbuilt function for that, so we can do this quite efficiently. You can see this already improves our selection by a lot. In the next step, we look at each column and only select the top pixel, since that is the layer we're gonna be interacting with. This gives us a pretty good idea of how the ground looks. But it's still just individual pixels. If we exaggerate it a bit, you can see that there's still a gap in between our data points. To fix this, we will need to connect them. The simplest way for that would be using lines. Especially if the dots are denser, it's a good and cheap approximation of the ground. But I opted for a spline interpolation because it gives better results for fewer data points. Now we can check the ground intersection for every trajectory. We compare the differences between the ground spline and the ballistic trajectory at a bunch of sample points. This trajectory we derived in the previous video, and it looks like this. If at any of the sample points the difference is small enough, we flag it as a collision. Now, we're not gonna disqualify these paths completely. There are some corner cases in which the path is still valid, but our detection system flags it as a collision. Usually you can kinda tell yourself anyway, so I think a warning is enough. As another piece of housekeeping, I also changed the way we output the trajectories. As I mentioned in the last video, we have to round our calculated power values, since in the game we can only set it to integers. So we inevitably have some error in the parameters. As a crude measure of how good a given trajectory is, we sort them by the rounding error, obviously preferring those with the least difference. I think implementing multiplayer and the ground detection were 2 important fixes to be able to actually use the aimbot in a real game. Now I want to dedicate the rest of the video to developing a model for the wind. While the model itself isn't terribly complicated or difficult to implement, as you'll see in a bit, I still learned a lot in the process, and I want to share that with you. Just in case you didn't know, in the game there is an option to turn on the wind obstacle. In between turns, the wind changes direction and speed, and depending on those parameters, it affects your shot. For example, shooting with the wind in your back kinda extends your shot, while shooting against it decelerates the projectile. So you have to shoot a bit differently than what you're used to. In the last video, where we've ignored the wind, we've derived this ballistic trajectory for our projectile. To be able to distinguish between the old and the new trajectories, I'm gonna write the old ones with capital letters. The combination of these two motions in the x and the y axis is what gives our projectile its characteristic curve. But if we shoot with the wind, we get a modified trajectory for which we will also need a formula. And whatever that expression is, will have to reflect the underlying physics. This situation we're in is obviously not unique to writing an aimbot. Oftentimes in physics, you have some experimental data, like for example the emission lines of hydrogen, for which you want to develop a theoretical model. So something that can correctly replicate the experiment, and ideally even predict its outcome. Again, in the example of hydrogen, this would be the Schrödinger equation, which we touched on in the last video about physics simulations. But in this case, it's the equations of motion for our shot. To get started with making a model, we have to make some observations and assumptions. You can't really conjure up a formula from nothing. Obviously, depending on what exactly you want to describe, you would approach it differently. For real life, this might be some physical laws or other theories you're trying to incorporate into your model. We, luckily, don't really need to deal with all that. Instead, we can just go into the firing range and play around with the wind. The first observation we can make is that the wind only blows along the horizontal, so the y direction isn't affected. Another almost trivial thing is that the wind depends on this parameter that I'll call the wind velocity Vw. Also, it only changes in between shots. So for our purposes, we can assume Vw to be a constant. The next 2 points are a bit difficult to show concisely in the firing range, so I'll just put up an illustration of what I mean. If you own the game, you can go ahead and convince yourselves that these 2 assumptions really hold. For the next point, we would want our description of the wind to also work for Vw equals 0, so the case with no wind. And then it should look just like the original trajectory. This makes sense if you look at low wind speeds and how the modified shot looks more and more similar to the one without wind. And lastly, what we see is that no matter the wind speed, the shots all roughly start out the same. Only as the projectile flies onwards do the paths diverge. So for small times, our path with wind should be roughly the same as without it. Depending on how rigorous you want to be, you could sit here and probably come up with a few more observations. For us, these 4 will be enough for the moment. Because at this point, I have a bit of a confession to make. During development, I made these 4 observations and came up with a model for the wind that seemed to fulfill them. I was really happy and kinda proud of myself that I found a good and realistic description of the wind, so I went ahead and implemented it. But after trying to run the Aimbot, it didn't work. I got unreasonably low powers, and even for small winds, the predicted shot would go somewhere completely different than in the game. Which is weird because it definitely fulfilled assumption 3. Yeah, that's like 5 hours of my life I'm not getting back. Now, there is nothing wrong with coming up with a false model. Before we test it, there is no way of saying whether it's accurate or not. But you should always be skeptical about your model. So instead of just showing you the right answer, I want to present you 3 potential candidates. One of them is obviously the correct one, while the other 2 are possible models, but ultimately wrong. Among those, that model that I went through all the effort to wrongfully implement. And together we'll try to correctly approach finding the right one. Let's get to know them. For all 3, we're kinda baking in observation 1 and 2 by only looking at the x-coordinate, and by having this variable Vw in the expressions. The alpha is just a scaling factor, which determines how strongly we react to the wind speed. This number we'll actually have to determine, similar to part 1. But for the theoretical approach, its value is irrelevant, so for now we can just set it to 1 and ignore it. The first one, that I call the acceleration model, assumes the wind acts as a force, pushing our projectile in the direction it blows. And the force pushing means having a non-zero acceleration. The second one, the velocity model, takes the wind as a velocity field. The wind is moving at a constant velocity, so it increases our projectile's velocity by that amount. And the third one, the drag model, imagines the wind as a particle stream with a given velocity. If our projectile is slower than those particles, they hit it from behind, effectively giving it a push. If we're going faster than the wind, we're bumping into the particles ahead of us, which slows us back down. This game continues until we're ultimately at the same speed as the wind. If you want, take a minute and convince yourselves that these mathematical expressions indeed reflect the behavior I was just describing. Now all we gotta do is see if they line up with our assumptions. Again, the first two are already baked in, so no need to check them. Because the screen is going to get a bit cluttered otherwise, let's just do the models one by one. Similarly to last video, we can integrate this expression twice and get a formula for the position. You might recognize this form to be very similar to the y-coordinate of our classical ballistic trajectory. This makes absolute sense, since there we also started with a constant acceleration. Now over to our assumptions. Here is what we would expect in both cases, just a simple linear trajectory. Up here we just set Vw equal to 0, and we can see that we can ignore the first term. If we compare it with our desired form, it matches well. So assumption 3 is fulfilled by this model. Let's check assumption 4. For small times, the behavior with wind should look about the same as without wind. But what does that even mean? If we just set t equal to 0, we don't really learn anything. Obviously at the start, I am at the starting position. And this is why we're not interested in how the trajectory looks at time 0, but how it looks at the very start. So instead, let's just set t equal to some very small number, like 0.01. Now something interesting happens. If we evaluate this square, we get 0.0001. Sure, it's multiplied by whatever constants, but I think you will agree that this contribution is much smaller than the rest of the expression. And this effect only increases if we make t even smaller. Here our expression only goes up to the power of 2. But the same idea holds for any greater power as well. Those terms become irrelevant even faster. So in the limit of t going to 0, we can ignore this quadratic term completely. Alright, so our first model already seems like a very good choice. It satisfies all 4 of our observations. But we can't rule out the other ones just yet. So let's take a look at the velocity model. Here I again calculated the expression for the position. It's even simpler than the last one. We look at the first row and set Vw equal to 0. This is easy enough to evaluate, and again we see the behavior fits. So what about t going to 0? Here we don't have any quadratic or above terms, so there is no need to simplify anything. But if we compare this formula to the one without wind, we see a bit of an issue. They differ by this term Vw times t. Only this time we can't ignore it. Even for small times, it will always be just as important as the other linear term. So this model doesn't fulfill assumption 4. Which, in hindsight, also makes sense. The bullet instantly gets the wind velocity added to it the moment it comes out the barrel. Which is a bit strange, because it just started feeling the wind, so why is it at full speed already? I guess it's still looking good for the acceleration model. So let's see if we can find a flaw in the drag model too. I'm just gonna say, getting to this expression here is not trivial at all. This is a proper, inhomogeneous second-order differential equation. For those who are interested, I'll put up the way I solved it, with a little trick to make the integration a bit easier. But now let's look at the assumptions. If in here we try to plug in Vw equals 0, and know that e to the power of 0 equals 1, we run into a bit of a problem. We get 0 over 0. Which not only makes all the mathematicians out there start feeling a great disturbance in the force, it also doesn't help us answer our question. But we can just look back at the original formulation of this model with the acceleration. If we set Vw to 0 in here, we see the acceleration is 0 as well. Which is exactly how we started deriving the trajectory in the last video. So it will necessarily have the same form. There are also other ways of showing it for first assumption 3, but I think this is the simplest one. Moving on, we want to look at the asymptotic behavior again. Here we unfortunately don't have t raised to a power, but instead e to the power of t. So what do we do here? Well, we can rewrite this exponential function as an infinite sum of terms like these. In a way, it's even the definition of raising e to a variable t. And this is a form we're more familiar with. We can again ignore all the infinite terms with order t² or higher. Now we just gotta simplify it a little and see that it satisfies assumption 4. Okay, so now we have two models which both fulfill all our criteria, but still look very different. So we must still be missing an assumption. I learned this the hard way, by having my aimbot not work at all, but we can try to be a bit more methodical about it now. How about we look at the trajectories the models produce, and how they compare to the one without wind. If our tank is down here at 0, 0, then the trajectory without wind looks something like this. The acceleration model goes a bit further, and the drag model goes further still. Everything as expected, since the wind carries the shot. Now, all these numbers don't actually mean anything right now, because we still haven't fixed the proportionality constant alpha, but it gives us something to look at. If we increase the wind speed, they both go even further, which is what we would expect them to do. But watch what happens as I decrease the wind speed. At first, both trajectories approach the neutral one. But if I reduce the wind speed even further, the drag model goes to the left of the neutral one, and then turns back around to approach it for wind speed 0. I think you will agree that this behavior is more than weird. Why does the shot without wind suddenly go further than with wind? And why do we have this weird turnaround in there? I'll say that this behavior is not unexpected if you look at the formula for the drag model. But it's certainly not what it looks like in the game. As you can easily verify there, any shot with the wind in your back goes further than the same shot without any wind. We can formulate this as our fifth assumption, which the drag model indeed fails to fulfill, as we've just shown. So I guess this seals the deal for the drag model. Lastly, I want to talk a bit about why the drag model fails here, and why it tripped me up when first writing the code. Initially I came up with this model because of the three it mimics reality the most. In real life we have air resistance, so a strong wind will not only carry a ball, it will also decelerate it if it's going slower. But in the game we've neglected air resistance from the start, so it would be a bit weird that it's suddenly there for the wind. Now, my expression is not the exact same formula as real air resistance, but the idea is still the same. And I guess if I thought a bit more about the implications of this model, like a shot falling off faster than without wind, I would have seen that it doesn't describe the behavior in the game. What I want you to take away from this section is to not blindly trust an idea, or in this case a model, just because you think it's correct. Always be skeptical and see if they hold up to the simplest of tests, like the one we did with the graphs. From here, the actual implementation is pretty simple. We just modified the calculate trajectories function to also calculate the power with wind. The proportionality constant alpha we can determine with a best fit algorithm similarly to last video. And it turns out to be pretty much exactly 0.001. All this maths here is just a rearrangement of the formula the acceleration model gives us. And from this we can calculate the needed power. Now I think all there's left to do is to put this aimbot to a proper test. So let me load up a game against bots. On my main screen I have the actual game, currently just waiting in the lobby. And off to the side here I'll pull up the aimbot. I wrote a simple game loop that prompts the user to input the wind velocity. If you have no wind, you just pass in 0. This integer then gets passed to the aimbot. And once we run it, it returns the calculated parameters. For the start, I'll just have 2 enemies because I found that everything gets a bit chaotic if 4 tanks all shoot at the same time. But don't worry, I'll also show off the full capacity in a moment. In the game, we can run the aimbot, and then it asks us for the wind velocity. So I'll just pass in -91. I have it so that the wind blowing to the right is a positive number, and if it's blowing to the left, it's negative. This way, it's consistent with our coordinate grid. I've paused the game for a moment so we can talk about the output here. As you already saw, we can detect our green tank and the red enemies. The blue curve is our ground spline, which is checked for intersections. Some of the trajectories are already flagged by that system, so we'll try to avoid those. Let's say I want to hit the left tank, Banjo. I have the output ordered that it starts with the leftmost tank, so we're looking for the parameters to tank 0. And I'll just pick the very first one. And just as expected, we land the shot perfectly. Usually it's best to just pick the first trajectory the system outputs, since they get sorted by their rounding errors. And this is also the path that gets drawn on the output, so you can even see your shot ahead of time. For me, it's still so fascinating that we can account for wind now. Especially for high winds where the path really gets curved to one side. Believe me, I had a lot of fun just playing around with the aimbot on my own. In hindsight, I'm also glad that we ended up with the acceleration model, because it still allows you to solve everything analytically. With the drag model, I had to do a lot numerically, which was pretty messy. Also, I have the ground detection currently capped at 50 data points, which then get interpolated. And as you can see, the spline still gives a pretty good approximation of the ground. I could easily increase this number, and it wouldn't even impact performance that much. But I just wanted to show off why I chose this or the linear interpolation anyway. To wrap up this video, let's switch to a full-on 4v4 match. I guess the question is now where to go from here. Well, some ideas come to mind, like implementing support for more complex weapons. There are some, like the Ringer or the Palm, where you need to hit a bit away from the enemy. Or there's a whole class of weapons that bounce a bit and only go off after a short delay. I'm not so sure on the bounce, but the different targeting should definitely be doable now that we have the ground detection. Then, on the topic of bounces, there are also different obstacles in the game. We have bouncers, health crates, or buffs to just name a few. Right now, they just mess up the detection, so I have them turned off. But you could try to incorporate them as well. But I guess for that, you really would need to switch to pattern matching, because just looking at the colors could get really messy. For now though, I'm really happy with this aimbot. I never thought you could get this accurate from only a screenshot. So at the moment, I don't really have an urge to explore these ideas. That is not to say I'll never return to this, but right now I want to focus my time on some different projects. This again turned out to be quite a long video, so I want to thank you all very much for watching, and see you in the next one.